Okay, so we can start now. Yeah, so I was saying that in last lecture on hardness, right, we saw some results where we showed that some problems are not solvable in polynomial time if p is not equal to np, right? So those sorts of results. So in this one also we'll see some kinds of some sort of hardness results, but they'll be different to what we did in the last class. Okay, so first we'll see this hardness of approximation of k-center problem. So like Saket said that we cannot do better than 2 approximation for k-center problem if p is not equal to np. Okay, and after that we'll see some concrete lower bounds. So by concrete lower bounds I mean proving something like some problem is not solvable in say order n square time, right? Something like that. So we'll be more concrete. We'll not be just saying that it is not solvable in polynomial time. We'll be giving some lower bound in p. So here first we'll see this hypothesis called strong exponential time hypothesis. Okay, and then assuming this hypothesis, okay, assuming that this is true, we will prove some lower bounds for two problems called orthogonal vector problem and diameter problem. Fine. So let's start with the first one, hardness of approximation of k-center. So I guess there is no need to like go over the definition again, but still, so yeah. So in the decision version of k-center problem, you get V, D, K, and R, right? Where VD is a metric space. And you have to tell whether there exists a k-center of radius R, right? And what is radius? Radius is basically maximum distance of an element from the nearest neighbor. Sorry, from the, okay, right? So this was the k-center problem. Now, if you remember, we gave a reduction from dominating set to k-center, right? So we'll prove this hardness of approximation for k-center using that reduction only. Okay, we do not need anything new. It's just like a few basic observations. So what was the reduction? So we took this instance g comma k prime of dominating set, right? And from that we created this v, d, k, and r. Okay, v was equal to just vg, the set of vertices of the graph. The distance or d was d of u comma u was equal to 0. D of u comma v was equal to 1 when u and v were neighbors, right? And d of u comma v is equal to 2 when u and v were not neighbors. Okay, k was equal to k prime and radius was equal to 1. Okay. And yeah, with this reduction, okay, for this reduction we can say that G has a dominating set of size k if and only if VD is a metric space with a k center f of radius 1. Okay. So suppose G has a dominating set of size k, right? Then we know that there will be a k center of radius 1, right? Now suppose G does not have a dominating set of size k. What will be the radius of a k center, minimum radius of a k center? Huh? More than 1, right? But what will be? Can you tell me a number? Sorry? So just look at this thing, right? That even when u and v, I mean, if you take u and v, right? If they are not neighbors, they are 2, right? So when G does not have a dominating set of size k, there will be a k center of radius 2, right? I mean, there will be no k center of radius 1, but there will be a k center of radius 2, right? Okay, so we'll use this observation in a few minutes to prove the hardness of approximation. Okay, so of course, if you are proving the hardness of approximation, we have to prove it for the optimization version of the k center, right? It doesn't make sense to approximate a decision problem because you all you have is a yes or no answer, right? So what is the optimization version of the k center problem? Given a metric space V and D and an integer k, right? You have to find a k that minimizes the radius, right? So this is the optimization problem, optimization version of the k center problem. And I think from the previous lecture we know that there exists a polynomial time to approximation algorithm for opt k center, right? What this means is that if for some V, D, and K, let's say the minimum radius possible is 3, right? Then this algorithm will give you at most 6, right? Some number between 3 to 6, right? Okay, so uh, in the last lecture, that can we do better than 2 approximation? So answer is of course no, and if P is not equal to NP, okay? So let's see why the answer is no. So suppose there exists a 1.999 some approximation algorithm for opt-K center, okay? And what we can do now is that we'll show that you can solve dominating set problem, the decision version of the dominating set problem in polynomial time using this approximation algorithm, okay? So here's my algorithm for dominating set, polynomial time algorithm. You take G comma K, right? You convert it into V, D, and K using the same reduction. And then you feed this V, D, and K to your 1.99 approximation algorithm of opt-K center, right? Now, what if G comma K is a yes instance? If G comma K is a yes instance, right, exists a dominating set of size K. Okay, so if there exists a dominating set of size K, what will be the minimum radius for V, D, and K? 1, right? 1. So if it is 1, what values can you expect here? From 1 to 1.99, right? Some value from 1 to 1.99, okay? Okay. Now what if G comma K is a no instance? What will be the radius of, what will be the minimum radius for VDK? It will be 2, right? I mean, from the reduction, it will be 2, right? So what values can you get if it is a no instance? It will be some value from 2 to 3.98, right? So can't you just like look at the value, the output of your 1.99 approximation algorithm and tell whether G comma K was a yes instance or a no instance? We can tell, right? Because they are disjoint, like, right? The values are not overlapping. Okay. So this is all. So basically, if you have any approximation algorithm, right, better than 2 approximation algorithm, right, then you can solve solve this dominating set problem in polynomial time. So I think in last class also somebody asked why I took 2. So let me go back just here, 1 second. Yeah, here. So suppose I change 2 to 3 here. Will it work? Like using that, can you still prove that you cannot do better than 2 approximation? We can, right? Because again, the intervals will be disjoint, right? But if I replace this 2 by 1.5, then it will not work. Because then looking at the value of your, like looking at the output value of your approximation algorithm, you will not be able to tell whether it was a yes instance or it was a no instance, right? Sorry? Sorry, one. Yeah, it will be. It will be. Yeah. I yeah. I think it will be a metric space. Yeah. Okay. So yeah, so all we wanted was that like this d of u comma v should be greater than equal to 2. That's it. If it is greater than equal to 2, then we can use it to prove this hardness of approximation for K center. Right. So this finishes the first part. Okay. So let's prove now some concrete lower bounds. Yeah. 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 Right. No, so because it is an approximation algorithm, it can give you 1.99 when the radius is 1, right? It's an approximation algorithm. So it can give you like something which is 1.99 times words. Yeah. I mean, you do not have, right? You know that VDK, right? It can have radius either 1 or 2, right? You know. Yeah. But this is an approximation algorithm, right? This algorithm, huh? Right, but I mean, I'm saying that, yeah. I mean, all I'm saying is that your given instance, right? If its radius is r, right? Suppose the minimum radius is r, then your approximation algorithm can give you something ranging from r to 1.99 r, right? So that's all I'm saying. Okay, yeah. Previous pair. So that's what we proved now, that sorry. Okay, you're saying an approximation algorithm for dominating set is possible, assuming this. I don't know. I'm not sure. Sorry. Okay, so yeah, so I was talking about lower bounds. So we have this hypothesis, right, that P is not equal to NP. Okay, and what this basically means is that 3 sat is not in P. Okay. Now there is something ETH, exponential time hypothesis. Okay, and it says something is stronger than P not equal to NP. What it says is that basically, forget about polynomial time. 3 set is not solvable even in 2 to the small o of n, where n is the number of variables. Okay. And we have something more stronger, something stronger than this, which we call strong exponential time hypothesis. And what it says is that for every epsilon, okay, greater than 0, there exists a k such that k set cannot be solved in order 2 to the 1 minus epsilon times n. Okay. So I wish I could tell you more about these hypotheses, but uh, unfortunately, I'm not the right person. I do not know much about them, but yeah, probably you can talk to other speakers if you want some more insight into these hypotheses. Yeah, little often. So you can do it in 1.99 n or whatever, but you cannot do it in root n. Okay, right? So of course, exponential time hypothesis implies p not equal to np, and set implies ETH. Okay. So what we will do now is that we will assume that set is true, okay, and assuming that we will prove, yeah. This one, this one. So basically, this implies this. Yeah. Okay. So maybe it will take some time. So all you have to do is like take some epsilon. Okay. Take some epsilon. Say like some 0.01. Okay. Then there must exist some k. Okay. Which will be, let's say, not solvable in time order of 2 to the 0.99 n. Right. So set is saying that k set, some k set is not solvable in order 2 to the 0.99 n. Okay. Then this will imply this small, it is a small o of n, right? You're getting this. It is not big o of n, right? So yeah, it is. So all I'm saying is that suppose this is true, right? That so for some k set you cannot solve it in order 2 to the 0.99 n time, right? Then this has to be true, right? Because if this is false, right, that is 3 sat is solvable in 2 to the small o n time, right? What you can do is that you can reduce that k sat to 3 sat in polynomial time, right, in some poly of n time, right? And you will have a algorithm that runs in just 2 to the small o of n time. Okay, but what we initially assumed was that it is not solvable even in 2 to the 0.99 n time. Okay.
So it means it requires 2 to the power n only. Does it mean that it requires 2 to the power n only? That doesn't say.
No, I mean, already saying is that, yeah, for every epsilon, you will have some k. such that K set is not solvable. Okay. Right. So yeah, so I was saying that assuming this set uh, that it is true, now we will prove some lower bounds for problems, for two problems called orthogonal vector problem and diameter problem. So let me quickly define what these problems are. So in orthogonal vector problem, you get two sets, A and B. Okay, so both of them are sets of some d-dimensional vectors. Okay, and both of them are of size n. And the problem is to find whether there exists x in A and a y in B such that they are both orthogonal. So x dot y, I believe everyone knows, but yeah, right, it is this. So you have to just multiply all the coordinates and then sum them, right? So can anyone tell me an algorithm to solve this problem? The best time that you can manage. Determinant. Okay, so, I mean the most stupid algorithm that you can think of, right? Every pair, right? So you try for every pair, right? So how many pairs will be there? N square. And for every pair, you'll be doing what? Some d many operations, right? No. So 1 second. It will be this, right? Some n square d, right? You have n square many pairs, right? You have n square many pairs, and for every pair you are doing some order d many operations. So your trivial algorithm will run for order n squared multiplied by d. So, okay, so here's the conjecture that you cannot do better than this. Okay, so for any epsilon greater than 0, it is not. You solve it in order n to the 2 minus epsilon times some polynomial of d. Okay, and this will prove assuming that set is true. Okay. What's the second problem? Yeah, so diameter. So diameter, given a graph G and an integer K, you have to find whether the diameter of G is K. Okay. So both of them are decision problems. Right? So given a graph G and an integer K, you have to find whether the diameter of G is K. Now what is diameter? It is just the maximum distance between any pair of vertices. Right? Okay, so here again, any guesses? N square? But how will you find the distance between every, you can go over all the pairs, right? But it's a graph, so you have to calculate the distance also, right? Shortest distance, huh? N cube, right? Yeah, okay. Right. So probably you can also get some runtime in terms of N and M using Dijkstra, right? And I'm not sure, like, depending on the value of M, sometimes it may be better than this or worse than this. But this is one trivial algorithm, we know, right? Just do the Floyd-Warshall, calculate shortest distance for every pair of vertices, and then you pick the maximum one, right? And here again, the conjecture is that order of n multiplied by m to the 1 minus epsilon is not possible, right? For any epsilon greater than 0. And this again, okay, so this one we will prove assuming this conjecture, the first one, right? So basically, if you cannot have a order n to the 2 minus epsilon times poly D algorithm for orthogonal vector, then we will see that we can also not have a order of nm to the 1 minus epsilon time algorithm. So let's start with the first one. So like I said, we will assume that set is true, right? So what was set? It was that for every epsilon greater than 0, there will exist a k greater than equal to 3, such that k set is not in time order of 2 to the 1 minus epsilon times n. And this is what we want to prove. If set is true, then OV is not solvable in order of n to the 2 minus epsilon times poly D for any epsilon greater than 0. Okay, so how do we do it? of course, if you are like using set to prove a lower bound for OV, then I think you can guess we have to give a reduction from, I mean, what do that would be give a reduction from SAT to, or K SAT to OV, orthogonal vector, right? So this will be our reduction. So we will take this instance phi, okay, of n variables and m clauses, and we will map it to an instance of orthogonal vector. Okay, so basically we will create these two sets A and B, where every, what's happening? Okay, yeah. So I was saying, yeah. So we have our phi, okay, and we are mapping this to, okay, yeah. So we are mapping this to A and B, okay, where A and B are both sets of d-dimensional vectors, where every coordinate of the vectors will be either 0 or 1, okay, such that the size of A and B will be 2 to the n by 2, right? And the dimension d will be equal to m. Okay. So any questions? Are the definitions clear, like of this set and orthogonal vector and all? Okay. And okay, yeah. So we will have this reduction, and we will do it in time this m times 2 to the n by 2, right? And of course, this reduction should satisfy this thing that phi is satisfiable if and only if there exists a pair of orthogonal vectors in A and B. Okay, so before we see the reduction, let's settle this here, that suppose we have this sort of reduction, then this proof we want to prove. Okay, so we'll be proving the contrapositive of this statement here, right? So suppose orthogonal vector is solvable. Suppose orthogonal vector is solvable in time order of n to the 2 minus epsilon times poly d. Okay, suppose it is solvable. Epsilon greater than 0. Solve KSAT this way, like what will be KSAT's runtime if you use this reduction, right? And this algorithm for OV. It will be, first you have to add the time for reduction, which will be what? M 2 to the n by 2. Okay. And you will also need to run this algorithm for OV, right? So algorithm that runs in time n to the 2 minus epsilon time times poly d. So just replace n by what? 2 to the n by 2. Okay. And d by what? M. Fine. So we are assuming here that epsilon is like very, okay. And I can say this, like we can drop the first term here, m multiplied by 2 to the n by 2. Okay. And we just like multiply the powers n by 2 and 2 minus epsilon and get that, right? Now what is m? Number of clauses, right? It can be how many? I mean, how many, at most, how many clauses you can have in a k-SAT problem? Some order n to the k, right? Right. So what I'm saying now is that if you like replace that m by some polynomial of n, right? Ultimately, you can get something like this: order of 2 to the 1 minus epsilon prime times n. But what this shows? This shows that if orthogonal, so it shows the contrapositive of what I have just written here. It shows that if orthogonal vector is solvable in order of n to the 2 minus epsilon times poly d, okay, then there exists some epsilon, right? There exists some epsilon such that for every k, k-SAT is solvable in time order of 2 to the 1 minus epsilon prime times n. Is this clear, or anyone has any doubt? Or okay, yeah. So okay, so assuming that we have this reduction, right? We can now say that yeah, this the statement that that we've written is true. So now let's see the reduction. So we'll take our phi and then convert it into A and B such that size of A equal to 2 to the n by 2 and each vector in A will be of dimension m. Okay, so here's how we will do it. So we have to create A and B. So for A, we take U, set U, which is set of all the assignments for variables from x1 to xn by 2, right? So basically the first half, set a set of assignments for the first half of the variables. Okay. And then we take V for creating our B, which will be the set of assignments for the second half of the variables. Okay. Now, how exactly we are going to create A? What that we will take one U, right, from capital U, and then we construct one vector for A. Now, as you can guess, the dimension of each vector is what? M. So let's list out all our clauses like this. Okay. And then we are going to create our A like this. Okay, so basically for every CIth clause, you will put either 0 or 1. Okay, and how do you put it? Any guesses? So if it is satisfying, okay, so if it is satisfying, then 1. Yeah, so suppose this U is satisfying CI. What should I put? 1 or 0? But what do we want in our OV problem? We want a pair of vectors which are orthogonal, right? And two vectors are orthogonal when for all the I coordinates, right? Both of them are not 1, right? Right? So we should put what? 0, right? So if U is satisfying Ci, then AI is equal to 0, else AI is equal to 1. And the same thing we will do for B also. Sorry? Yeah, so U is a set of just all the like 2 to the n by 2 many assignments. So assignments for variable from x1 to xn by 2. Yeah. Then it will be, I wrote na, else AI equal to 1. So if it is, we are putting 0. Yeah, not satisfying, right? So if U is satisfying, then AI is equal to 0. Otherwise we will put AI equal to 1. Okay, so I guess I think the proof is also very clear, should be clear now, but still let's do it. So forward direction. So forward direction is what? So we are assuming that phi is satisfiable, right? So there must be a satisfying assignment for phi. Let's say it is W. Then from W, let's define WA to be the first half of W. Okay? So WA is the first half of W, and WB is the second half of the W. And if we have these assignments, there must be some vector corresponding to them, right, in A and B. So suppose we have A and B, right? So vectors corresponding to WA and WB. Now can there be an I such that both AI and BI are equal to 1? Like, does there exist an I such that the ith coordinate of both A and B is equal to 1? It's not possible, right? Because we some assignment is not satisfying CI, right? So if there exists an I such that both AI and BI are equal to 1, what this means is that both WA and WB are not satisfying that clause CI, right? But we know that W is satisfying CI, so either WA or WB should be satisfying it, right? So that means this thing cannot happen. That for no I, both AI and BI will be equal to 1. And that means what? They are orthogonal, right? So this side is right, is fine. Okay, so the other side is also quite similar. So suppose now we have two vectors, okay, which are orthogonal. Now again, since we have two vectors, there must be some assignments corresponding to them. So again, let's take W and WB. Okay, so they are the assignments corresponding to A and B. And again, I claim that if you concatenate these two assignments, you will get a satisfying assignment for phi. Right? Because if A dot B, I mean, it's just repeating the same thing again, but if A dot B is equal to 0, right, for every I, at least one of the coordinate of, right, at least one of the, either AI or BI will be equal to 0. And what this means is that either WA or WB must be satisfying that clause CI. And this you can say for all the clauses. So this proves what? So yeah, so this proves the other direction. So anything about it? Okay, so let's move to the last part of the talk. So lower bound for diameter. So this I said, so yeah, diameter is the problem. There we're given a graph G and an integer K. You have to find whether the diameter of G is K, right? And this we want to prove that if orthogonal vector is not solvable in time order of n to the 2 minus epsilon times poly D for any epsilon greater than 0, then diameter is also not solvable in time order of nm to the 1 minus epsilon prime for some epsilon prime greater than 0. So we will be reducing orthogonal vector to the diameter problem. So we'll take some A and B instance of orthogonal vector problem and we map it to G comma 3 here. Okay. So this graph G will have some order n plus d many vertices. Okay, and some order dn times some order dn many edges. And this reduction we will do in order dn time. Right. So here again, I mean, before seeing the reduction, so suppose that there exists such a reduction and see why what we have written is true, right? So again, here we'll prove the contrapositive of what we have written, that if orthogonal vector hypothesis is true, then you cannot have such a running time for diameter. Okay, so suppose diameter is solvable in order nm to the 1 minus epsilon time. So just replace n by what? N plus d and m by dn. Okay. It will be something like this. And then you can further simplify it to this. Order of n to the 2 minus epsilon prime times poly of d. Fine. So what this shows, this shows that if there exists an order of nm to the 1 minus epsilon times algorithm, right, there exists some epsilon prime greater than 0 for which you can solve OV, right? OV in time order of n to the 2 minus epsilon times poly of d. Okay. So this is clear, or anyone has any doubt? Okay. So let's see the reduction then. Okay. So what we will do in G is that we will take our A from the orthogonal vector instance, okay, and for every vector in A, we create a vertex in G, okay, and same thing we do for B, right? So we have how many? Some 2n many vertices, and let's set some more vertices for dimension, okay. So if D is a dimension, we will have some d many vertices in the middle, okay. Now how can we add edges here? So let's see it by an example. So suppose V1 is this, right? 1, 0, 1 followed by all zeros, like lots of zeros, and it ultimately ends by 1. Okay. Then I'm going to do the following. I'm going to draw an edge from V1 to some vertex J in C if the jth coordinate of V1 is 1. Okay. So this is what we have to do because like we have only 3 ones. So we will have 3 edges from V1 to 1, 3, and D. And we'll do the same from the other side also. So W1 is a vector which has only 1 on the second place and the last place. So we will draw 2 edges from there. And this we will follow generally. Like we'll put an edge from Vi to J if the jth coordinate of Vi is 1 And similarly, on the right hand side, we will put an edge between wi and j if the jth coordinate of wi is 1. Yeah. No, 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 no. So this is instance of the diameter problem that so basically what we are going to show now is that if there exists a pair of orthogonal vectors here, then the diameter of G will be 3. Just that. Uh, it is not. 1 second. So this is not the complete graph. Maybe this is not complete yet. Okay, so I mean, once it is complete, probably we can see it. Okay, so yeah, so like I said, the reduction is not complete, but can we say the following? The distance of two vertices, right? Say Vi and Wj. So Vi is in A and Wj is in B, right? It is equal to 2 if and only if Vi and Wj are not orthogonal. This we can say, na? Because if they are not orthogonal, right, they must have some coordinate k, right? So Vi and Wj will have some coordinate k for which uh, both of them will be equal to 1, right? Because otherwise their product will be equal to 0, right? So this we can say. Okay, so let me make some more modifications to this graph. So of course this is not complete because right now the diameter is not 3. Right? I mean, there are some vertices which are not even connected. Right? So what we will do now is that we will make some modifications in such a way so that apart from two pairs which are supposed to be orthogonal, right? Every pair, like distance of every pair will be at most 2. Okay. So this is how we are going to do some modifications. Yeah. Sorry, it is not Vi minus A. It is just like you put an edge from Vi to J if the jth coordinate of Vi is 1. Yeah. Sorry, I mean, yeah, I agree. It's a bit confusing. Okay, so yeah, so I was saying that on this graph, now we will make some modifications in such a way so that the distance of any pair, except those who are orthogonal, we'll see what we can do for orthogonals, right? Except for those pairs which are orthogonal, the distance will be at most 2. So how we can do it? So let's add these two special vertices, say Y and Z. And what we are going to do now is that we will add one edge. We will add one edge from every vertex in A to Y. Okay. And then again, we will add an edge from Y to every vertex in C. And the same thing we will do for Z. Right. So this is the complete reduction. I mean, our graph is complete. So now just check, like, is the distance at most 2 between any pair of vertices apart from those who are orthogonal? So suppose, suppose we take Y. Okay. Uh, can we reach every vertex of this graph in distance at most 2? Right? So, I mean, every vertex in A, it can reach in one with just one edge, right? Every vertex in C, it can reach in one step, right? Every vertex, uh, 1 second. Okay, it is not complete. What happened? Yeah, this is the couple. Sorry. Now it is complete. Sorry. Yeah, every vertex in B, you can reach in 2 steps, right? And of course, Y to Z, Z to Y, you can reach in 1 step. Okay. Same thing you can say for Z. Now let's look at the vertices of C, right? Here again, every vertex in the graph, right? Even including the vertices of C, you can reach in at most two edges. Agree? Right. So what is left now? Vertices from A and vertices from B, right? Now we saw earlier that if Vi and Wj they are not orthogonal, then the distance will be what? 2, right? Because there will be some coordinate k via which you can go from Vi to Wj, right? But what if they are orthogonal? 3, right? So this, right? So suppose V3 and W2 are orthogonal, right? Still you can reach in 3 steps from V2. I said V3 and W2, right? Yeah. So from V3 you can go to Y. From Y you can go to Z and then to W2. Right? So distance. So now we can say the following, right? That the diameter of G is equal to 3 if and only if there exists a pair of vertices which are orthogonal. Right? Yeah. Yeah. Previous slide. So we want this. Okay. Yeah. So this thing, right? That we have this graph, right, of this size. Okay, and and the reduction time is dn only. Okay. So if we can do this reduction in this time and of this size, right? The reduction is this, that there exist a pair of orthogonal vectors, okay, if and only if the diameter of G is 3. Okay. And I mean, these things are important because you have to ultimately show that if diameter is solvable in this time, order of nm to the 1 minus epsilon, uh, then orthogonal vector is also solvable in order of n to the 2 minus epsilon times poly of D. Right. Okay, so any other doubt? Because this is the last slide. Okay, then. Thank you. Yeah. Five per tide. Uh, yeah, you can say that. Yeah. Yeah, I think. Yeah. Okay. Thank you.